Okay, hi everyone. So we're back to doing this, but it's going to be pretty short, this topic. This is going to be the start of area of study 2. This one is going to be on light and matter. So our last area of study 1, that was on waves and stuff on how we could treat light as a wave. What we're going to be doing over the next 3 or so lessons, like I said, short topic, is going to be stuff on light as a particle. You can see looking up here that that's the name of this lesson. And we're also going to look at matter and waves and light, how they interact with each other. That's going to be part of this. And the TV is apparently going to keep doing that, so it's going to be a bit of a nuisance. But quick area of study. This is a short one. There'll be an assessment task at the end, but I've still got to get that organised. Hopefully with the white on black, it's going to be a bit easier to view. Let me know if it's still kind of a hassle. I'll be putting these PowerPoints up on Compass, so yeah, you can always use them off there if you want to go through those. So what we're looking at today are 2 things. Well, really one thing. We're looking at the photoelectric effect and how it gives us evidence that we can treat light as a particle. Now, we've gone over this before, that for a long time, people debated whether light was a particle or was it a wave. Last year of study, we looked at things like diffraction, which was really the only one left now that they took all the old stuff out of the study design for this year. But the idea of that was that we looked at how light could be explained as a wave. We looked at the double slit experiment and how light was doing things that it wouldn't do if it was a particle. That was the gist of our first area of study. This one's about looking at the behaviours of light that can only be explained if we treat light as a wave, as a particle. So that's what we're going to be focusing on today, and it's going to be in contrast to our last area of study. It says down there, some behaviours of light can only be explained using the wave model and some can only be explained using the particle model. Because of this, we say that light displays what we call wave-particle duality. In some situations, it does things that can only be explained if it's a particle. In some other situations, it does things that can only be explained using the wave model. We say it shows a bit of both. It's not purely a particle, it's not purely a wave. It's got wave-particle duality, and this area study is where we look at the particle aspect of that. So, when we treat light as a particle, we're thinking of it as just being a clump, and that clump, this one piece of light, that's just what we call a photon. So in the same way that we have one electron, or we have one proton, we can have one photon, just one bit of light. I'm recording this, right? It'd be silly if I wasn't. So a photon is basically like a particle of light. That's the terminology we use when we talk about light as a particle. And we can talk about the energy of a photon. It's going to be found using this equation here, E equals hf. E is the energy of a single photon. F is going to be its frequency, just in hertz like we've seen before. H is going to be a new thing which we call Planck's constant. It's just a number that we use in this area of study quite a bit. There's 2 different ways of expressing it. The first one is using this number here. It gets given a H just for its variable, its letter. And it's going to have a value of 6.63 times 10 to the negative 34 joule seconds. The unit's not so important, the number, you use it quite a bit. So that's one way of expressing Planck's constant. But when we're dealing with photons, we're dealing with very, very small energies. And often, when we're dealing with energies on that scale, we switch over to a different unit which you probably have not seen before. What we're going to be using is called the electron volt, or which gets given the symbol a little e next to a big V. It's just a different unit of energy, just like the joule is the unit of energy. The electron volt is also a unit of energy that we use. It's like, feet and meters. You're talking about the same thing. You're talking about length. It's just a different way of describing a different system. And the gist of the electron volt is that if you've got an electron and you accelerate it through a voltage of 1 volt, that 1 electron is going to gain 1 electron volt worth of energy. So that's where the name comes from. 1 electron through 1 volt, it gains 1 electron volt of energy, hence why it's called so. And we relate it to the joules by saying that 1 electron volt is going to be 1.6 times 10 to the negative 19 joules. So it's going to be considerably less than a joule. Joule is like an everyday unit. How much energy does it take to boil water? That sort of thing. Electron volts are much, much smaller because we're dealing with much smaller energy scales, but we can use these when we talk about electron energies, photon energies, just like we're going to be doing. So to do your conversions between electron volts and joules, I've written it up here. convert joules to electron volts, divide by 1.6 times 10 to the negative 19 to convert electron volts to joules, multiplied by that same factor. So you've got your conversion factor here. A quick check is that if I've got like 10 electron volts, I know that that is not very many joules. So if I'm not sure if I'm supposed to divide or times it, then a quick check is to just go to myself, well, I'm supposed to get a very small number of joules from 10 electron volts. If I times it by 1.6 times 10 to the negative 19, I get a very small number. If I divide, I would get a very large number. So you can either remember just how to convert, or when it comes time to convert, just use a bit of practical sense and see if then you expect a small number and you get a big number, then you probably should have times when you divided, or vice versa. So I said before, Planck's constant, 6.63 times 10 to the negative 34 joule seconds. That's one way of expressing it. The other way is writing it converting that from joule seconds to electron volt seconds by dividing by your conversion factor. And we get 4.14 times 10 to the negative 15 electron volt seconds. So we're going to use both these values, and the one we use is going to depend on context. I'll kind of point out when you can use this one. Normally by default you use the 6.63 negative 34 one. It's like the standard units one, but sometimes you just get a question where if you plug in the electron volt second one, you save a couple of steps, you save a bit of time because you don't have to do conversions as much. So this one's like your default one, but there are special times when you can use this one and just speed up whatever process you're doing. You won't have to convert if you can just use that one. Okay, so basic example. You've got a photon, it's got a frequency of 514 hertz, and you want to find the energy of that photon A in joules and B in electron volts. So for the first one, I'm going to find its energy in joules by using the equation of a photon's energy from before, E equals hf. I've got my h, I've got my f, I multiply those two things together and I get out my energy in joules. Now for the second one, finding in electron volts, there are two ways I could go about doing this. There's the long way, where I do part A, find the energy in joules, and then convert that answer to electron volts by dividing it by my conversion factor, 1.6 times 10 to the negative 19. That's the long way of doing it. That's like two steps. The alternative way of doing it is that you use this equation, but rather than using your joules seconds version of Planck's constant, you use the electron volt seconds version of it, the 4.14 times 10 to the negative 15. And if you do that, then the answer that you get out from HF is going to be in electron volts. So that's basically the gist of it. When you use this equation, if you use this joule seconds version, your answer comes out as joules. If you use this electron volt seconds version, your answer comes out as electron volts. So depending on what form you want your answer in, that's going to basically determine which one you would probably want to use. Of course, if I found this one, I can convert it to that one. If I found that one, I can convert it to that one using the conversion factor. That's introducing an additional step, which you can always do. It's just a bit quicker to just pick the right one and get your answer that you want out straight away. Okay, so for light, in our last area of study 1, we had this equation that the speed of light is equal to the frequency of light times the wavelength. We can rearrange that equation so that the frequency is on its own. Then we take our equation from before equals hf, substitutes that c over lambda is f, and we get out an equation for the energy of a photon in terms of its wavelength. So this one, Planck's constant is a constant, speed of light is a constant, wavelength is the only variable in there. So it basically gives you an equation showing how if you change the wavelength, it shows you how you would calculate the energy of the photon based off that. So the example is just a photon has a wavelength of 500 nanometers. What is the energy of the photon in joules? I plug in my Planck's constant, I plug in my speed of light, I plug in my wavelength, 10 to the negative 9, and get out my answer in joules. I know my answer is in joules because I use this joule seconds version of Planck's constant. Again, if I'd use the electron volts second version, my answer would have been in electron volts. But I just wanted the answer in joules, so I plugged in the joules seconds version. So now, all that stuff that I just talked about is background to what we're doing today. It's just going to set up the concepts that we need to really get into what comes next, which is about the photoelectric effect. Now, what I've written up here is that there's one phenomenon that you can't explain using the wave model of light, and that is the photoelectric effect. And the basic idea is you've got a piece of metal, shown in this diagram. You've got a piece of metal here, and well, I guess what you really have here, I'm not sure how clearly this is coming in. You have to check the compass PowerPoint to see this picture if you can't see it clearly on the video. But we've got some battery, we've got a voltmeter and ammeter. They're not so important, but we've got a bit of metal here and a bit of metal here. And what happens is that there's light being shone on this bit of metal. We call it the cathode. That light is sometimes going to cause electrons to jump out of the metal, and sometimes it won't. Whether or not electrons jump out of this metal and travel across the gap, it depends entirely on the wavelength of this light. So you're shining light on this cathode, electrons might jump out for certain wavelengths, they might not jump out for other wavelengths, and that was something that couldn't be explained using the wave model of light. Like, if light's a wave, why is it showing this particular behavior? So that's the gist of the photoelectric effect. Photo meaning light. Take a photograph, it's about using light. Electric to mean the flow of electrons, electricity. You put them together, you've got the photoelectric effect. And just a bit of terminology, we use the word photoelectrons to talk about electrons that are released by the metal due to the photons hitting them. So photoelectrons, it's a word that often gets mixed up with photons because they're pretty similar. You just need to keep in the back of your mind that photons are the bits of light. Photoelectrons are electrons given off by the metal because the light hits it. And we just call the flow of the electrons from here to the other side photocurrent. It's a current, it's caused by the light. Those two words come together and get you photocurrent. Yeah, take a drink. Yeah. I realise that the camera's spazzing around quite a bit, but it's probably the best that I can do. So it's found that if the frequency of the light was at or above a particular value, you would get the electrons getting released from the metal. If the frequency is below that value, you're not going to get any electrons emitted. So we've got a cutoff value. If the frequency is higher than that cutoff value, you get the photoelectric effect. If the frequency of the light coming in is below a particular value, nothing happens. You stand there looking at a circuit where nothing's going on. We call that cutoff value for the frequency the threshold frequency. It gets a little F subscript 0 when we talk about it. So it's basically if we've got a bit of metal and we know our threshold frequency, we'll get the photoelectric effect above that frequency. We will not get it below that frequency. So now I've got to try and multitask. Let's see if I can get this going. Is that going? It's gone. Awesome. So this is basically showing what we've got. We've got our external power supply here. Hopefully this can be seen clearly. If not, you can always just access it from the PowerPoint, bring it up and just give it a run yourself. I recommend it. I normally like to get students to actually pull these up and just play around with them, get an intuitive sense of how changing variables affects what's happening. But I guess we're a bit limited in terms of doing that. I'd recommend it though. Go to the PowerPoint that's on Compass, download the PowerPoint, go to this link that's from one of the slides and just, do what I'm doing. See how your changes to it affect what you see. But you've got your bits of light coming in. You can see that they are just in packets. It's not like continuous waves coming in. So we've got one photon coming in. The photon hits this bit of metal, which happens to be sodium in this case. This will be the cathode. And it's going to release electrons. So we've just got a parade of electrons leaving the cathode heading towards the anode. So what happens is that if I change the frequency of the light, I'm lowering it to lower and lower frequencies. Eventually I'm going to get to a point where, they'll be pretty precise about this, you can see that I'm not getting any electrons, hopefully you can, anymore. If I was careful, I could find an exact frequency where I no longer get electrons coming out. So I'm below the threshold frequency, and so as the light shines on the cathode, nothing's happening, no electrons being released. That's just what I'm expecting if I'm below the threshold frequency. If I'm above the threshold frequency, then it doesn't matter how high above I am, as long as I'm at it or above, electrons are going to get released. That's just all the threshold frequency tells me. And there's a bit to unpack involving the photoelectric effect. So just like when we did the double slit experiments, we've got the basic qualitative ideas of what's going on, but then there's also a whole heap of maths relating different variables that are involved in it. So we're just going to have to cover those too. Frequency is above the threshold frequency. Yeah, that's it. So if you've got the frequency above the threshold frequency and you increase the intensity of the light, that's going to increase the current. And if the frequency is below the threshold frequency and you increase the intensity, there's not going to be any current still. I might jump back. I could have reordered these a bit better, but... can I change the intensity? Yep. So on here, there's no thing that says intensity. Instead, it just says photon density, which is just the same thing. When we're talking about the intensity of light, and we're talking about the particle model, intensity is just how many photons are coming in. The more intense the light is, that just tells you you've got more photons coming in each second. So if I up the photon density, you can see I'm getting more and more photons coming in. They look like they're moving faster, but you should know that they're moving at the speed of light. It's just that there's going to be more of them coming in, and I guess they show that by speeding up the process. And if I have a low intensity, you can see that they're coming in less and less, getting less photons per second. That's what lower intensity tells me. So if I'm above the threshold frequency, I'm all the way up here, and I think the threshold frequency was back here. Changing the intensity changes how many electrons are going to flow, and if you remember your electricity stuff, the number of electrons passing a certain point per second just tells you your current. So the more intense the light is, the more electrons are going to get released, the higher a current you're going to see. If you are below the threshold frequency, so all the way down here in the red, doesn't matter what the intensity is. If I crank up the intensity to the max and light's just pouring in, if I'm below the threshold frequency, it doesn't matter how many photons are coming in, I'm still not getting any electrons coming out. So that's the gist of the threshold frequency and its relation to intensity. If you change the intensity below the threshold frequency, nothing changes. If you're above the threshold frequency and you change the intensity, that changes the currents that you're going to get out. So jumping back, switch across. So all that stuff that I just said, we basically tied into why the photoelectric effect can't be explained using the wave model. So if light was a wave, then as more light shone on the metal, as more intense light was shone on it, it should be given energy. So energy should be given to the metal, and eventually enough energy should be there for electrons to be emitted. So if you think of light as being a wave, then think of it as like waves in an ocean or something. You've got energy pouring in, more and more energy pouring in. Eventually the electrons should get enough energy that they can jump out of the metal. But like I just said, that's not the case. If you're below the threshold frequency, it doesn't matter how many waves or how many photons you send in. If you're not above the threshold frequency, you don't see any effect. So that's kind of something the wave model can't really explain, why it is that if you keep sending in energy, you don't get electrons emitted. So that's just a particle model of light, and the explanation is basically this. You've got a single photon that hits the metal and interacts with a single electron in the metal. So you've got your metal, it's made up of protons and electrons, as any metal is going to be, some neutrons too. A photon comes in, hits an electron, interacts with it, and it either gives it enough energy that that electron can jump out of the metal, leave the cathode, or it doesn't give it enough energy that it can do that. So it's going to be one of those two cases. Either the photon that comes in has enough energy that the electron can jump out of the cathode and leave and move along, or it just plain and simply doesn't have enough energy. So that's just a particle kind of explanation, because we're dealing with one fixed thing that's got a certain energy amount. That's just a particle concept. We can't talk about waves in the same way. Also, if light was a wave, there would be a brief delay between the light hitting the metal and the electrons being released while the energy accumulated. So if light's a wave, it sends in energy and it keeps sending in energy, and eventually there's enough energy for it to jump out. There'd have to be a delay while that energy accumulates at the electron, but that's just not what gets seen. It's basically the photon hits, boom, the electron's either out or it's not. There's no build-up of energy, it's just energy is transferred from photon to electron. There's no time for it to accumulate. They've done really precise measurements of this, so it's not like there's a sufficient time frame for that to happen. Yeah, that's the last one there. Okay. So just like before, if you can't see this, look at the PowerPoint on Compass. But one thing that I haven't mentioned so far is we've got our voltage source up here, and we can change the voltage. Particularly, we're going to be concerned with how we change the strength of it and also the direction. So up here, I've got my positive end here, and so my anode here connected up to the positive side of the battery is also positive. Here I've got my negative side of the battery connected to the cathode. So what happens here is pretty intuitive, I guess. You get electrons, they jump out of the cathode. This side's positive, that side's negative. They get pulled towards the positive, they get sent away from the negative. The electrons just get pulled towards this side. Nothing particularly weird or noteworthy about that. It's what you'd expect to happen. Current's about how many electrons are passing at a certain point each second. There's still the same number of electrons being released, so the current's going to remain the same. So if you've got the battery set up like this, nothing's really going to be different. You're going to be measuring the same current on your ammeter. You're just going to have some faster moving electrons as they get accelerated from one side to the other. So that's one battery setup, and that's not the one that we're really going to be focused on. What we do though is we reverse the battery, negative here, positive here. So now this is positive, this is negative. As electrons leave the cathode, they're going to get pulled back towards the cathode, they're going to get pushed away from the anode. So we've got the battery reversed, and as a result, having this reverse battery setup, there's going to be some force that once the electrons leave the cathode is going to be pushing them back towards the cathode. Now, I really like this little animation, assuming I've picked the right one. This one, beautiful. This is the second one I want you to have a look at if you can't see it up here, because playing around with it gives you a more intuitive sense of what's going on. But in the event that you can see it, you can see that we've got some purple light. Purple's got very high frequency, so it's almost always going to be above the threshold frequency, so we're getting electrons released. You can see that electrons are just basically flowing out of our cathode towards our anode. Down here, we've got our battery, and just like before, if I put that into positive, I think, you can see that they're getting pushed away by the negative cathode and pulled towards the positive anode, so they're just speeding up as they move. There's nothing particularly noteworthy about that. What's kind of fun though is that if I put it in the negatives, you can see, maybe, I don't know, that the electrons leave, they're getting pulled back towards the positive, pushed away from the negative, and so they just don't reach the other side. So because of our negative, there's a word for it and the word keeps escaping me, I just got the negative setup. The electrons that are released just don't reach the anode, and there's no current flowing as a result. Now, I'll have to jump back to that. Now, before I talk about that a bit more, I'm just going to provide a bit of context for what's, because if you're observant and if you can actually see the stuff on the screen, you might have noticed something in the demonstration I showed you. The idea is that within the metal, the electrons are bound to the metal, and they need some energy to be ejected from it. So that's what our photon's doing. It comes in, gives some energy to an electron. It might be enough energy for it to leave, or it might not be, depends on the photon's energy. But that's what's happening with the electrons. They're getting energy and they're being ejected from the metal. Some of the electrons are less tightly bound than the others, and they need less energy to be ejected. And the terminology that I like to use is called they're the less tightly bound electrons. It's not really formal terminology. You don't have to talk about least tightly bound, but it's how I think about them. So within the metal, you've got some electrons that are stuck into the metal really tight and would need a whole heap of energy to get out of the metal. Some electrons aren't bound that tightly, and they need less energy than others in order to escape. The ones that need the least energy in order to escape are just what we call the least tightly bound electrons in the metal. So when an electron leaves the metal, it's going to have some kinetic energy, maybe, with the least tightly bound ones having the most energy. So if you imagine you've got a whole heap of electrons bound within a metal, and light of the same frequency comes in, it'll give each photon of that light is going to give all its energy to one electron. If an electron is not very tightly bound, it's going to have enough energy to leave the metal, and it's also going to have maybe a bit of energy left over that it got from the photon. So all the energy of the photon goes to an electron. Some of that energy goes towards the electron leaving the metal, and sometimes there'll be some leftover energy that the electron's going to have from the photon, and that's going to be in the form of kinetic energy. More kinetic energy it has, faster it's going to be moving. And it says here, and I'll jump back to the thing, applet from before to show how this works. As the negative voltage is increased, less and less electrons can reach the anode. Eventually, even the least tightly bound electrons are stopped by the voltage and no longer reach the anode. The voltage at which this happens, we call that the stopping voltage. Now, jumping back, that's what you can kind of see here. If I set this to 0, so it's in the middle, you can see that some of these electrons are moving faster than others. Some of them are moving kind of slow, some of them are moving a bit faster. That's just because some of these electrons are more tightly bound than others. If they're more tightly bound in the cathode, then when they come out, they're going to have less energy than the ones that aren't bound as tightly, that aren't as strongly held within the metal. So as a result of that, you just get a bit of a distribution in terms of the speed of the electrons after they leave. But if I increase the voltage, you can see that, no, you can't see, I've set the voltage too high. Let's try 0.6 if this thing will move. 0.8, let's try 0.4. Sorry that this is so finicky. If this is boring, then just speed up past this. Figure out how to do that in your videos and you'll probably be golden. Come on. There we go. So I've set it to 0.2, which hasn't done a whole lot. Yeah, it has actually. So you can see like this electron, is it going to get there? No, it's not. So some of the electrons, now that I've got minus 0.2 volts, some of the electrons can still get to the other side. They've got enough energy that they can cross, but some of them don't. Some of them get to about here and turn back. So that makes sense. Some of the electrons have more energy than others. Some of them can go further than the ones with less energy. So when there's this repulsive force, it's only going to affect some of them, not all of them. So as I increase that negative, I might up the frequency as well, just to make this look a bit better. So as I increase the voltage, so now I'm at minus 1.8, I'm still getting like this electron and that electron, they're getting to the other side, but most of them are only getting to about here and they're getting turned back. So now I've got less current reaching the anode because less electrons are able to get across that gap. I'm still getting some current, I think it says on there the current, because some electrons still have enough energy to reach the other side. But eventually, I'm going to set this to such a voltage that, yeah, now none of the electrons are able to get from the cathode to the anode. So I'm registering 0 current just because I've reached a voltage where there's too strong a repulsive force from the anode and too strong an attractive force from the cathode that none of the electrons can get to the other side. So I've reached what I call the stopping voltage. It's a voltage at which none of the electrons can get to the other side, and it's one of the quantities that we look at in a fair bit of detail. How long have I been talking for? A while. When we look at the photoelectric effect. So stopping voltage, just the voltage at which the electrons are completely stopped from getting to the other side. I don't want to talk for too long because, well, I get tired when I do. But just this bottom picture basically shows a few things. We've got the voltage that's being applied, like the battery slider that I was changing before on the horizontal axis. We've got the current that you would measure on the vertical axis, and we've got two lines, one corresponding to a low intensity, one to a high intensity. So you can see when you've got a higher intensity, you're going to get a higher current. You've got more photons coming in, more electrons getting released. So more electrons traveling across that gap means you've got a higher current. But you can see that regardless of what intensity you have, they're basically going to meet at this point where if you get to a certain voltage, none of the electrons are going to be able to cross the gap. This voltage is just what we call the stopping voltage as a result. So this is just a graphical depiction of everything I was just saying. If you change the intensity above the threshold frequency, you change the current, but regardless of what intensity you have, there's going to be some voltage at which you stop getting any current, and we just show that as the negative, as the point there. It's a negative because it's just going to be a negative voltage. Okay. So far there have been two main factors when describing the photoelectric effect. You've got the frequency of the photons and the voltage that you're applying to your circuit. And the other main factor is the metal that's used as the cathode. So when I had up my example before, I had a sodium cathode. That was the metal that made it up. But you can use any metal as your cathode and you're going to see the photoelectric effect, I think. I don't know if there are any exceptions to that rule, but generally metals have that property that they'll emit electrons when there's enough frequency for the light coming in. So when we talk about metals, we're talking about something called a work function. And the work function is basically how much energy do you need to put in to get electrons out. What's the threshold frequency of the photons that you need to get in, and what energy corresponds to that frequency in order to get the photoelectric effect actually going on. So the work function states the minimum energy needed to release an electron from the metal. And like I said, that energy is coming from the photons, it's coming from their E equals HF. You can find the energy that the photons have if you know their frequency. And then if that's above a certain value, you'll get the photoelectric effect going on. I might have to record this across a few days because I'm just starting to feel it. So, for example, work function of sodium is 2.36 electron volts, and that means that if a photon is hitting a bit of sodium, that photon needs at least 2.36 electron volts for you to get electrons being released from the metal. If it's below that value, you won't get any electrons released. If it's above that value, you get electrons released and they'll be moving faster because they've got a bit of extra kinetic energy left over. So those were our three things. We've got the frequency of the light that's coming in. We've got the voltage that's being applied between the anode and the cathode. And we've also got the work function. What kind of metal do we have and how much energy do the electrons in that metal need to get ejected? So we use this little phi symbol for, I think it's a phi, showing the work function. Don't know if I mentioned that before. In your books, this is tilted and it looks a bit nicer. So if you see that symbol and it's tilted, it's just the work function. And we define the work function in terms of the threshold frequency by saying, well, HF naught, that's the energy of a photon that is at the threshold frequency. E equals HF, and F naught is the threshold frequency, so this is the energy of a photon at the threshold frequency. And that's just going to be what the work function is, how much energy that metal, the electrons in that metal need in order to be released from that metal. So the example is, you've gone back to sodium because that's old reliable. It's got a work function of 2.36 electron volts. We want to know what its threshold frequency would be. What's the minimum frequency that it has to have, photons have to have for the photoelectric effect to occur. So 2.36 electron volts. Now this is in electron volts, so I'm going to pick my electron volt second version of Planck's constant to use times the frequency, the threshold frequency. So this is one case where if this is electron volts, then I'd pick that electron volts seconds version of Planck's constant, and my numbers will end up working out okay. If I wanted to be safe and a bit more, well, I guess safe's the word, I could have converted 2.36 electron volts into joules and then used the joules second version of Planck's constant, but I chose to use a shortcut here and said this is electron volts, so I'm going to use this particular version of Planck's constant, and it'll just work out for my numbers. So I rearrange my equation, divide 2.36 by Planck's constant, and I'm going to get out 5.7 times 10 to the 14 hertz. Mentally, you don't need to be able to do this, but it's always a good check. This is just about the frequency of visible light. So no one in your head that, come on, I've got to hit that before it turns off. No one in your head that you're dealing with frequencies of roughly, 10 to the 14 hertz when you're dealing with visible light. It's just a good background check. If I got out 10 to the negative 10 hertz or something, I could mentally go, oh, hold on, something's gone wrong. This is much too low a number for my answer. And then I might double check my working and see that I haven't put some calculation error into my calculator. If I missed those brackets and didn't have those on there, I'd get out a different number than I'd want. So it's good to be able to do those checks when you know roughly what your answer should be looking like. Also, we're talking about the voltage, and it's going to be basically doing some work on the electrons as they move. If you remember, work is just the change in object's energy. So the change in energy of the electron due to the voltage is going to be equal to the charge of the electron times the voltage that's being applied across that gap. Now, if we take that equation and put in the stopping voltage, then we can figure out that when we've got the stopping voltage set between the anode and the cathode, then if an electron starts out with a certain amount of energy, all that energy is going to get taken away from it by the stopping voltage. So that's what the stopping voltage is. It's the voltage at which electrons aren't going to reach the anode and there won't be a current flowing. If that's the voltage that we've got in place, then it makes sense that however much energy the electron started with, all that energy must have been taken away. All that kinetic energy must be gone because they're moving, slowing down and stopping, then turning back. The field is basically just taking away the energy that the electrons must have started with. So this is the energy taken away from the electrons that started with. It can be deduced that this is equal to the amount of kinetic energy that the least tightly bound electron started with. Remember from that little applet I had up before, some of the electrons could reach the other side when I put a voltage in place. Some of them could not. The ones that were least tightly bound to the metal, they had the most kinetic energy when they escaped the metal. So that meant that they were able to travel further, go faster. They could get to the other side when other electrons couldn't. We can figure out the energy of those electrons by which we just call EK max, the maximum amount of kinetic energy that the electrons must have started with. And we can relate that to the work done by the field, by the voltage. So just using a bit of logic, if it starts out with this much energy and it loses all its energy, then this must be the amount of work done on the electron by the field, or vice versa. If we know the stopping voltage and we calculate the work done on the electrons by the voltage, we can set that equal to the maximum kinetic energy that the electrons must have started with. We can relate this and that, which I don't think I've done. Maybe I've done that later in the PowerPoint, but I think it's done in terms of words rather than an equation, that this and that are going to be equal. This and that are going to be equal to each other. So if we know the stopping voltage and you're asked a question about the maximum kinetic energy of the electrons, you can just say this is equal to that and do a calculation based off that to find your answer, your maximum kinetic energy for the electrons. A different way of looking at it is that the maximum kinetic energy that the electron has when it leaves the metal, it's going to be equal to the amount of energy that the photon gives it when it comes in, take away however much energy that electron needs in order to leave the metal. So it's equal to, according to our equation, maximum kinetic energy of an electron is equal to the energy of the photon as it comes in, subtract the work function, the energy that the electron needs to leave the metal. So this is just our equation, and we do a bit with that. We use it in a few different ways. But that's all it really tells you conceptually, that we've got the energy of a photon coming in, gives some energy to the electron. Electron needs some energy to leave the metal, and the difference between those two energy values is going to be how much energy the electron has left once it's left the metal. That's going to be its kinetic energy. I got this graph up. Why did I put this graph up? I have to have a think, have a drink. That's right. So here what I've got, I'm not supposed to go for more than 40 minutes. So I'll try and speed the rest of it up, although I'm feeling a bit drained. I've got purple light and I've got red light, and you can see that the purple light, it's got a larger stopping voltage than the red light. That's just because purple light has more energy. It's got a higher frequency than red light. So the electrons that leave the metal, if there's purple light, are going to have more kinetic energy. There's going to need to be a larger voltage in place between the anode and the cathode to stop them reaching the other side completely. So changing the frequency is going to affect our stopping voltage. Higher the frequency, the more energy the photons have coming in, the more energy the electrons can have when they leave the cathode, the higher voltage we'd need across the anode and the cathode to stop the electrons getting from one side to the other. So that's just what that graph's telling you. And last of all, and I used to do a SAC based around this. Don't know if I'll do it this year. Actually, in hindsight, I probably will. So, keep this stuff in mind. It's important. We've got our equation. EK max equals HF minus the work function. We can express that as a graph. So our y-axis is EK max, as you can see on here, maximum kinetic energy of the photoelectrons. And our horizontal axis is going to be the frequency. We've got a times 10 to the 14 hertz because, like I said, typical value for the frequency of an electron. Now this equation is basically the same as our y equals mx plus c equation. We've got our vertical, we've got our horizontal, and we've also got our gradient. In this case, that's going to be h, Planck's constant. And we've got our y-intercept, which in this case is going to be the work function. So I think I've said that. So we've got two lines drawn here. One's going to be for potassium, one's going to be for magnesium. You can see that they are parallel to each other. And that's going to be because, well, the slope of this line should be Planck's constant. The slope of this line should also be Planck's constant. From that, you should be able to figure out that they both have the same slope, so they're going to be parallel to each other. The way that they're different from each other is in terms of their y-intercept. You can see the y-intercept of potassium's a bit above -4, maybe -3.8, and the y-intercept of magnesium's about -6. So this is times 10 to the negative 19 joules. Normally this might be in electron volts. I prefer graphs that do have that on the y-axis, but make do with what I got. So basically what this tells us is that for potassium, our y-intercept, -3.8 times 10 to the negative 19 joules, that's going to be the work function of potassium. That's how much energy an electron in potassium is going to need in order to leave that potassium cathode. For magnesium, it's going to be a different metal, so a bit different work function. The electrons in magnesium are going to need -6 times 10, 6 times 10 to the negative 19 joules in order to leave the magnesium metal. So we've got our different y-intercepts, just representing visually the different work functions of those two metals. We've also got last bit, I think it's the very last bit, the horizontal intercept, where these lines are crossing our horizontal axis, and that just tells us the threshold frequency for that particular metal. So for potassium, visually I can figure out the threshold frequency, the minimum frequency for electrons to be released from a potassium metal. That's going to be about 5.2 times 10 to the 14 hertz. Magnesium, it's got a higher threshold frequency at about 8.8 times 10 to the 14 hertz. So again, it's just basically you get a graph and you're expected to deduce information from that graph based off your equation and how it can be represented graphically. I think that's it. So that was a long lesson, but the photoelectric effect, there's a lot involved in that, so you probably need a bit of time in order to unpack all that. So you should just be getting on with those questions. They're from chapter 10. I'll put a lesson plan up on Compass with the questions, and you should be doing those and the checkpoints questions. I know it's a fair bit to us, but you do want to also make sure you're doing a bit of Ed Rollo stuff, just to make sure that you're showing me that you have an understanding of the material and that you're actually doing stuff while we're away from school, so that I know you're actually working. Although if you do want to just send through some sort of, however you want to do it, indication that you're doing your work, then that's all fine by me. I just kind of need to know that you are actually working from home and meeting those outcomes so that I can give you S's. So that's basically it. You should just be getting on with your